Good afternoon, everyone. My name is Siva Poornan, and good afternoon, everyone. My name is Siva Poornan. I'm a doctoral student at the Civil Engineering Department of IIT Madras, and here we are meeting for the last time in this course uh, to discuss on matrix method of structure analysis regarding any queries that you would have, and in general about the content and concepts. So, in the previous weeks, we have been discussing on how to analyze structures using matrix methods, and specifically we started, like, in the first few weeks we just recapped on basic structure analysis. Then we went on to displacement methods, and we built on matrix methods, starting with trusses first, then on beams, and then on frames. And then we also slightly touched upon the concept of shape functions, which are important, especially when you go on to FEM and then take a course on FEM, you would study it in detail. In the last week, we saw a few conceptual problems that would help us to understand structure analysis better, because from this course, we have been learning that we can incorporate matrix method into into an algorithm. We can build an algorithm and then put it into computer coding so that it can automatically formulate everything, given the uh, given we are able to say the members orientation and so on. So this commercial softwares are widely available, you might be familiar with them, and so we can use them for analyzing any complicated structure. What is important is that we need to have a sense of intuition, and we should be able to know whether the answers that we are getting is making sense or not. At last, it's just going to give you the solution for what you're going to input. So if there is a mistake, we need to know that there is something wrong in it. So that's why we discussed on some simple problems and see whether we have some sense of intuition in the answers that we get. And in this session, we will be talking partly on finite element analysis, going towards building towards finite element analysis, and see how do we switch over from matrix method of structure analysis to finite element. What is the difference, and what are we going to? Why do we need them, and so on. And partly we'll be again solving some interesting problems that I have noted down for you, so that you can try to guess what would be the deflected shapes and other static response like bending moment and shear force for some structures. Interesting problems. So before we get started, I would like to know if there are any questions from previous discussions or from the course.
Yes, from previous discussion, after
Yeah.
question number 4, we can discuss. I have tried it at home. We can verify
Okay.
it.
I
And then
can you
also,
say what question number 4 is, because
yeah, I can present it. You can just take a screenshot.
yeah, so
Or
is it the same
it's,
structure that we had discussed
yeah,
as
yeah.
before?
Last,
Yeah.
which you had left for us to practice.
Okay, then can, yeah, you can probably show it here so that we can draw it again here. Or
Yeah.
even I
The
might have it.
screen share now. Can I share it? Yeah. Okay, is it visible?
Yeah.
Okay, so this were the question. You can take screenshot and then maybe you can share.
Okay, is it a cantilever beam
It,
with
it was
central
a
loading?
soft cantilever. There are a lot of questions till question number
Okay.
11.
Okay, I think I have the questions here.
Yeah, you have the questions in the resources.
Yeah, right.
Yeah.
Right.
So you
Yes.
can maybe
So we can,
present
yeah,
again.
we can start from here itself then.
Yeah. Stop. You have
Good.
to present again.
I think I'm already presenting, if I'm not wrong.
It is not coming in full screen. Yeah, yeah, now it's.
Actually, you might have to pin it. So, but that's fine. I have reshared it again so that you can see now. I hope, right?
Yeah,
Okay, fine. So in these, maybe we can finish these questions and then go back to basics of FEM,
yeah.
right? Fine. So, what is the deflected shape that you guess for this problem, and what is the
At
shear
the
force bending
fixing, the
moment?
slope would be zero. At the far end, it will be. a slope. There will be slope
Good.
and
Before, yeah, at the fixed ends we anyways will have the slope as zero. But what is the shear force and bending moment that you would expect? Yes. Yeah, fixed and bending moment is zero is what you're saying, or slope is zero?
fixed and slope is zero.
Slope is zero. Okay, that's known. But it's a determinate beam, right? So what is the fixed end moment for this beam?
Fixed end moment would be P into L minus
Yes.
P by 2
Yes.
into 2L.
So what is that?
That is zero.
Zero. So can you draw the bending moment shape for this figure?
That is zero. So till here,
So
uh,
if this is a
from
beam,
P
it's
by 2 to up to P,
yeah,
it will be P into PL by 2.
PL by 2 at this point, right?
Yes.
So it will be PL by 2 hogging or sagging?
It will be
Positive or
hogging.
negative? It will be
Oh, sorry,
sagging, right?
sagging. Sagging, yeah.
Yes. So it's sagging and then it will drop from this
It will
point
drop
to
from this
0.
point to 0.
So it is positive. Entirely it's sagging, right?
Yes.
Now, so what is the use of the fixed end in this problem then? What is the fixed end even doing? And before going to that question,
Mhm.
what is the deflected shape for this figure? It seems very interesting, isn't it?
Yes.
This bending moment looks like what? Looks like for which
That
structure have we seen this bending moment?
uh, simply supported with point loaded bit.
Yes, so the supports this is same. Only instead of this fixed end, we could as well have a hinge support,
Mm-hmm.
and that would have the same bending moment shape, right? So
Yes.
then, what is the bending moment shape what is the deflected shape for the structure? The first question. Second question is, what is the role of the fixed end? What is the fixed end doing there? If we know that the fixed end is going to be fixed end moment is going to be zero.
Mm. Yeah. Never thought of it like that.
Okay, so can you guess the deflected shape?
Deflected shape should be from intuition should be slope at slope at a fixed point. The slope should be zero.
Yes,
Following it, there has to be some slope. Okay,
yes,
and at near the load point, the tangent has to be zero.
yes.
So you connect
So
it smoothly, then you get the deflected shape.
okay, so are you saying something like this? Yeah, maybe I'll change the shade color. Yeah. Is this right?
Mm,
We know
yeah,
it's sagging. Do you
yeah.
expect the deflection here to be zero or not?
Yes,
Yes.
deflection
Why?
here to be
Why should it be zero?
no,
So
no,
basically,
deflection. No, not the deflection. The slope. I was
slope.
expecting it to be zero
Why should slope be zero?
near the near the load point
Yeah. What at the load point? Why do you expect the slope to be zero?
because comparing it to the simply supported.
Ah, that is a different. That's what we need to be careful about. So, comparing the bending moments and comparing structures, we can only compare strains and curvatures. We cannot compare displacement and slopes because displacement and slopes would depend on boundary condition. Okay, we have seen this already, I guess. For example, if we have a cantilever with the end moment, this is same as so this curvature would give something like this, right? So this would give zero slope at this point, right?
Yes.
Now, if I can say that, okay, this free body diagram is this, right? Now I can compare it with a simply supported beam with a similar, with a loading such that it has same free body. What will be the deflected shape?
Yeah.
So here slope is zero at this point. Is it not? Both are different points, right? The slope
Yes.
at this point is not zero. So what is the same between them is the curvatures at this point and curvature at this point would be the same. Or in other words, if I take this beam and then rotate it, I can get this deflected shape.
Hmm.
Both are overlapping is what we can know and not the exact displacements. Displacement here is zero. Here also it's zero, but rotation is not zero. Rotation is zero here. And at this point, we see that there is a maximum deflection, but maximum deflection happens for this beam at the end.
Yes.
So there is a displacement and the rotations we cannot directly compare. It's only
Hmm.
the curvatures and strains that we can compare. Okay, so that you need to be careful. So what we have to know is that the deflection it's totally sagging moment, which means that it will have a sagging curvature, it will
Curvature.
have maximum deflection at this point, because it will sum up through the curvatures will sum up throughout from the fixed end to the free end, and so it will have maximum deflection here. And then we know that since it is totally sagging, it will have uniform curvature. So starting from this point, you can just say that that is all.
Mm.
Okay, so this is, you know, that it is like a bow, like what you said last time, right? So
Yeah,
we, from this we can only know its shape, but not exact displacements and rotations. It
exact
can have a
location.
rigid body rotation in addition to the way simply support would deflect. So
Okay.
therefore, if you compare it with the simply supported deflection from the midpoint, it's just rigid body rotation of that
Mm.
here. Okay, so that is all is the deflected shape. Any doubts on that?
So where the deflection has will be maximum,
Where should be maximum?
it has to be at the load point,
It,
midpoint.
at the midpoint?
It
At, at
because the slope is now zero at the far end. The deflection, the central deflection should slightly shift towards the right of
can you
the
please say that again?
uh, because the slope has. I'm speaking geometrically, okay.
Okay,
So because the slope is zero at fixed point, okay.
okay,
So the starting point of curvature has been shifted towards right. So the
yes.
deflection has also is also to be maximum slightly towards right of the load. I think so.
So where are you saying the deflection would be maximum?
Uh, Slightly right of the load, mid load.
Why deflection is maximum here visibly, right?
No, actually, I'm thinking this question as a prop cantilever from the starting.
And
that,
so
that is
a
why. It's
load is entirely different from
yeah.
support.
But if you talk this question as a prop cantilever, then
A
that should be
prop
okay.
a propped cantilever would have entirely different thing, because
Yeah.
we don't know the support
No, actually,
reaction.
when I saw this question, I solved it as a prop cantilever. I thought this
That
as a prop cantilever.
that is exactly why I wanted to give these questions, is that we should
Mm.
know a difference between support condition and free body, or
Mm.
support condition and forces. So what is given is the force P by 2.
Yes.
If you solve it as a propped cantilever,
Then
if
it
you
will not
solve,
be pivot.
the unknown reaction will not be P by 2, may not
Pivot.
be, can be exactly P by 2, but
Mm.
I guess it will not be,
It will not.
right? So if forces are given, the values are known, those are forces,
Mm.
they are not supports. If supports are given, their values would not be known to us.
Yeah.
Okay, and if the load is exactly equal to the support reaction of a propped cantilever,
Mm.
then exactly, even if the load was given or the support was there, the deflection here would be zero.
Mm.
So
Yes.
what I'm trying to say is that in a propped cantilever, the support reaction would be that amount which would make the deflection zero,
Yes.
right? But here,
Mm.
since it's given as p by 2, we need not, it need not happen that the deflection there
Yes.
be zero.
Basically,
Okay.
I changed the boundary condition.
Yes, yeah, the boundary condition is
What changed?
not propped cantilever. Yes, so it's a cantilever. That's it.
Okay. Okay. Fine.
So that is what you need to be careful of, whether it's a support condition or a load. Has to be very
Mm.
clear. Fine.
Okay.
So the deflected shape at this point would be maximum here. It's a cantilever
Yeah.
with a uniform moment. So
Mm.
all the uniform means same sign moment. Since it's positive throughout the span, all the curvatures will lead to increase in deflections, and the deflections
Mm.
would be maximum at the end point. That is all it is, right?
Okay.
Then coming to the question of what is the use of the fixed end.
Fiction is acting there as a boundary, maintaining the slope to be zero.
Yes, so it is just making the structure to its rigid bodily rotating this curve to this. It's just rotation of this to this.
Mm.
Okay, such that the slope here becomes zero. So why the slope has to be zero is the role of fixed end. Nothing else it's doing. It's just rigid bodily rotating this beam to this. That's all it's doing. and it's not. It's very free to do that. It doesn't have any. It doesn't require any moment to do that. In
Hmm.
this particular case, it depends on the forces. If the forces were different, definitely moment would have been produced,
Hmm.
depending on, right? So even if we remove the fixed end at this point, nothing will happen to the structure. It will still stay still as like this. But the only problem is that if the load slightly change also, it will become unstable. Because if you just remove the fixed end, what it means is that the new structure is this,
This is a
right?
bar.
Yeah,
Hmm.
it's just one side support you have as hinge.
Yeah. Beam with one support.
Yes, and it so happens that it will be stable because you don't need any moment at this point. The moment
Hmm.
due to P and the moment due to PP2 would exactly cancel at this point.
Yeah.
So it will be in equilibrium, but it's not stable. Why it's not stable is any disturbance of the loads will lead it to non-equilibrium. Therefore, it is not a stable position. So
Yes.
a fixed end would ensure that it is a stable structure.
Okay.
Okay, is that clear?
Yes.
Okay, so then we can move on to the next problem.
Yeah.
You have any questions from this? Do you want to continue in these problems or
No,
we
no, no.
can?
Now it's clear.
Okay,
Actually,
I
I was
mean, okay,
playing around with the boundary condition.
yes, yes, okay. So,
Okay.
should we continue with these conceptual questions or should we go to FEM and then come back to this?
Yeah, we should go to FM, I think, because it will
Okay,
take
then
time.
we'll
We
just
can
keep
come
this on
back.
hold and then we'll discuss the main concepts for the session today and then we'll come back to
Also in
this.
ATM, I have some questions, but I will ask them progressively.
Okay, yeah, fine. So, now, coming back to the main topic for today's session, what we are going to discuss in this is just introduce the concept of finite element analysis and see what it is and why do we need it. How does it make our life simpler? How does it help us to do solve problems in an easier way is what we are going to discuss. We will not discuss all the details of finite element analysis here. It's just how finite element is built and basics of it, just the introduction of it is what we will be seeing in this session. Fine. So first thing to note is that in all structural engineering problems, whatever problems we have in practice can be idealized to a model, and those models will give rise to differential equations. For example, even if you note in axial beam problems, stress problems, or in stress problems or in beam problems, you would note that you would get a differential equation that has to be solved. For example, we would have the double integration formula, right? So that itself is built from uh, Euler's formula, right? And that is basically a differential equation. We know that moment is equal to, this would be well known to us. Moment is equal to m by ea is equal to curvature, right? And curvature is nothing but actually double differentiation of deflection. So this is nothing but an if m is known as a function of x, right, and y is also a function of x, right. So basically now we have what we have is a differential equation. This differential equation has to be solved with certain boundary conditions, and that would give rise to what is the total deflection at any point. So basically we would have, but every problem would can be converted into a differential equation which has to be solved. For example, we'll just take a example case study here. It's a variable area member which is subjected to axial forces. As you can see, it is subjected to two types of axial forces that just for sake of demonstration we have drawn this. One is an n force F and one is a distributed force of Q of x, which varies with x. Okay, x is the span starting from here. Okay, so area is also varying, the force is also is varying. Now how do we formulate a differential equation for this? So what we do is that we take a small infinitesimal element, right, which is at a distance of x, distance from the reference point. Okay, and the span itself we will take it as dx, small infinitesimal element, right. So if we just take the small element, what would be the area of it? It will be just A of x, A at the position of x, right? And what are the forces that it would be experiencing? At the right end it will be experiencing, let's say, q of x plus dx, and to the left there might be some axial forces which would be just q of x. And what would be the I'm sorry, this is not q, this could be some other forces. We don't know the internal forces, let's just denote it as some sigma. Okay, these are the internal forces that would be there in this area. Okay, and what would be the force uh, that is happening in this area? It will be q of x, right, at that position of x. So now if we see from equilibrium, what does equilibrium say? Equilibrium says that the difference between these two forces, what is the difference between these two forces? It's d sigma of x should be equal to, it's the difference should be equal to minus q of x, right? Is this right? So this is what would be the equation that we would be getting. So from equilibrium we can say that actually we have to equate the area. So I'll just equate the area here. Area would be d sigma of x into area of x, right? That would be equal to q of x into dx, right? So that's what equilibrium says to us. So these are the internal forces and these are the external forces, both should be equal and opposite for this element to be in equilibrium. So from this equation what we see is that we have got an differential equation of this. How do we know that? Because we know that stresses are related to strains in a particular way, right? So for example, sigma is nothing but Young's modulus times the strain of x, right? So when we substitute that, what we get here is that a of x. So I'll skip of x here because it's known, it's understood. So a into d, e I will take outside because it's a constant, it's not going to vary with x. D of uh, strain, right, is equal to, sorry, minus q into dx, right? So now I can find out strain also. Uh, I know it's nothing but dy by dx, right? So if du by dx, if u is the displacement at any point, then epsilon is nothing but du by dx. So I can say, write it as Ea into, if strain is written as du by dx, then differentiation of that will just become u double dash, right, is equal to minus q, where I have written d epsilon by dx as u dash, u double dash, right? Why? Because we know that d epsilon by dx is equal to d square u by, okay, that's what I have used here to write this. So now why we did this exercise is to show that the structural engineering problem has again become as a differential equation. We have to solve this differential equation to find out what u is, right? So similarly most of the problems that we have at hand can be converted into a differential equation, right? And how do we solve these problems is that we need to have some certain boundary conditions to solve it, right? So in this particular case, from the fixed end we know that u of 0 should be equal to 0. And what else do we know? We know that the force is at this point equal to F, right? And what is force? Force is nothing but sigma at the position of L into area at the position of L, at the location of L, should be equal to F. And sigma is nothing but again E times epsilon, and epsilon is U dash. So using all that we can write A into A, we can take it that side. So sigma is nothing but E times epsilon at L is equal to F by A at, right? And epsilon itself is U dash. So this is another condition we have, and this is the first condition that we saw. These are called as boundary conditions because they say what happens to the boundary. Boundary is the extreme points of an element, right? So when we took this element, x equal to 0 and x equal to L are the two extreme points. So we know something about them. At one point it's a free surface, so we know what is the stresses occurring. Another point it's a fixed point, so we know what is the displacement occurring at that point. So basically we have in both the boundaries we know something and we use those boundary conditions, and we need to solve this differential equation and then use these boundary conditions to solve for the differential equation. We might have studied how to solve differential equations in engineering mathematics, right? But not always mathematical solutions would exist for differential equations, right? Sometimes it becomes very complicated and sometimes it's possible that there is no solution existing, right? So under those situations, what do we do? How do we solve a differential equation if it is very complicated to solve it directly, or it is impossible to solve it directly, right? So under those situations we have some methods called as approximate methods, right? So where we are trying to only find out an approximate answer for it and not exactly find an answer. We are, as engineers, we are happy with some little error happening in it and we are okay with it. We just want a solution of it, right? So uh, there are some methods called as approximate methods, and we'll discuss on that now, right? So this is how we actually go slowly towards FEM. So what in this slide we are going to see is that how do we solve for equations for which there are the differential equations are difficult to solve. So let's take an example here. Let's consider a differential equation that's given here. U double dash means d square u by dx square, okay? And let's say this is an differential equation we want to solve. Actually this differential equation is not very difficult to solve. Exact solution exists for it, okay? It's given as 1 by pi square into sine pi x. But then let's assume that we don't know it. Let's assume that we don't know how to solve this differential equation using the mathematical principles. Then what do we do is what we are going to discuss here. So what we do is that we just assume a function for u, right? So we can assume anything that we want. So let's assume that u is of the form, a quadratic equation would be a very good case. In the sense it would be a very good starting point, right? So I can just say that it is a plus bx plus cx square. I don't know what is the solution for this, but I'm going to assume that it will be of this format: a plus bx plus cx square. Where what I'm interested in is I'm interested in finding out ABC such that the error of this between the actual solution and the approximated solution is minimum. So basically my problem now is to find out ABC such that u is not a very bad approximation for this problem. U is a good enough approximation for this problem is what I want to find out, right? So what is the error function? Error function is the difference in error, difference in the solutions assumed and the actual solution, right? So what is error function is, I will define error function as E. I'll denote the error as E, which is not to be confused with Young's modulus, right? So maybe we can change the notation. ER would be the error, okay? Now this error I'm defining it to be, I'll take this u, I'll double differentiate this. Okay, if I double differentiate, what do I get? If I differentiate it once, I get b plus 2cx, right? Now if I differentiate it again, what do I get? I'll just get 2c, right? So I know u double dash, which is approximated, is 2c. But I know that u double dash should be equal to sine pi x, right? Negative of sine pi x. If it was right, if the solution was right, then it should satisfy this condition. So the difference is, error is nothing but 2c is u double dash of this thing, and actual u double dash should be equal to, so I can say is equal to minus of sine pi x, or what I can say is error function is minus 2c minus sine pi x. This is what is error function. Why I'm writing this way is, if u double dash is actually equal to minus of sine pi x, I can rewrite this equation and I'll write it as minus u double dash minus sine pi x equal to 0, right? Now if we have assumed an exact solution, then u double dash would become equal to this and the whole thing will become equal to 0. But since our assumption may not be accurately right, so we have u double dash to be equal to 2c. So I'm just substituting 2c here. So 2c minus sin pi x will not be equal to 0, but it will be equal to some error. That's what I'm writing here. Clear? So error is equal to this thing is what I have. Now what I want to ensure is that the total error needs to be minimized, right? So what can I do? Let's say the actual function u is varying with respect to x in certain way. Okay, so let's say this is x and this is a solution u. Let's say this is the accurate solution. We don't know this, what function it is. Actually, it is 1 by pi square into sin pi x, but let's say that we don't know this. We are just approximating it to a quadrilateral, right? Quadrating is like a parabola. So this is approximated. I'll use blue color for approximation. So let's say this is an approximation. Now what is error is? Error is just the area between these curves. So the difference is what I'm taking, right? It's not area. The difference is what I'm taking. If you see here. So the error is what I'm defining here, right? This is what error is. Now if I try to minimize this error, the problem is that positive portions and negative portions will cancel with each other. Is it not? Because at certain points 2c might be greater than sin pi x and certain points 2c might be lesser than sin pi x. So if I add everything up, it might show that the error is 0, but actually there is a finite error. As we can see, it's not actually, the blue curve and the black curves are not exactly the same. So in order to make error to be 0, we should actually, we cannot directly say that the error has to be minimized, but we have to take something like least square, right? So what we have to take is that we have to take something as some weight function. What is weight function? I'll just say, let's just say that error function into error function. Okay, now if this total area summation from 0 to L, in this case it's just 0 to 1. Okay, 0 and 1 are given as the boundaries, so L is nothing but 1. This error into error functions total summed up for dx, if we minimize this thing, then we are good to go, right? This is what we want to do. We want to minimize this area. Why error into error is so that it becomes error square, which will be always positive irrespective of whether it's negative or positive, right? So we will just denote this whole thing as error square. So what is error is already known to us, so we can just take square of this. Okay, so I can write it as minus 2c minus sin pi x, the whole square dx. I have to minimize this. If I have to minimize this, minimize with respect to what? The only variable that is there in my control is c, right? Because c is the only thing that is a variable here. I can only change c, right? So I have to differentiate with respect to c. So I'll just write differentiate with respect to c and make it to 0. So this is just an equation which I can solve, right? I can solve this equation and then I can find out what c is. Once I know what c is, then I can also use boundary conditions and then substitute. Basically I can find out the displacement function that is required, that gives an approximated form of this this differential equation, right? So this is a general way. I am not going into the details, but this is what is the broad way in which we can be used to approximate functions, approximate uh, differential equations and find out answers for that, right? Now what I had said earlier was that we can minimize 0 to L. I said error function into error function, right? But we need not always have error function into error function. We can have different forms of it. So in general, what people do is that instead of using error function into error function, we can just take some weight function into error function. Okay, but this weight should not be 1. Why? Because if weight is 1, then we are just minimizing, trying to minimize error, which will not be actually the case, because positives and negatives would get cancelled. Okay, so there are certain norms in which we have to pick up this weight function, and one of the things that we already saw was that weight function can be error function itself, right? That's what we saw earlier, and this method is what we called as a least square method, because it will just become error square, right? And another popular weight function is to use for the whole thing. It is just to use u of x itself, weight as u itself. Okay, so if we use that, then that method is called as Galerkin method. Okay, instead of weight being equal to error, we can use weight being equal to the displacement itself. If we use that, then we actually what we end up with, the differential equation, the equation that we have to solve is what is called as a Galerkin method. Okay, there are different ways in which we can solve. I'm not getting into the details, but that's different methods are there, and these two are the most popular ones that we solve, right? And when we solve these equations, we what we end up is the approximate solution that would be satisfying the differential equation in a very approximate, basically we are minimizing the error. So for the assumed solution, whatever is the best match we can get is what we will get. So it all depends on the initial assumption that we take. We, instead of taking a quadratic equation, I could have taken a cubic equation, or I could take a linear equation. I could take any form of equation that I want, right? So the advantage of taking a higher order polynomial is that I will end up with many variables that I want, a, b, c, and so on, right? So since I'm ending up with many variables, I would have many choices. I can approximate the function in a better way, right? So that is the advantage of taking many coefficients and ending up with a higher order polynomial. But then that will increase the cost of how we solve it. It will take more time for us to solve it. Okay. So usually what is preferred is to take a linear equation. Take a plus bx. Okay, this is what is preferred. But what is the problem here is that we would have a higher error. We would have a lesser approximation. We might not be able to get a very efficient match for it. Okay, then the problem happens, the problem, so we anyway this will reduce the computational cost, so we might want to go up with this. But then the problem is, sometimes it is not possible to just assume u is equal to a plus bx. The reason is that the differential equation that we might be having might have a higher order, it might have a higher order in it. So let's say you have a double differentiation happening here, then you cannot take u equal to a plus bx, because when you double differentiate it, you might not end up with something like c2c, but you will end up with 0, because you are taking a linear polynomial, right? So just because the differential equation, the original differential equation has a double order in it, you might not be able to assume a linear function to approximate it. That is why we what we do is that there is something called as modified Galerkin method, in which we will integrate it by the give a given differential equation, we will integrate it by parts and try to reduce this order of integration. Okay, I hope you would be familiar with the concepts of integration by parts. It's not very difficult. So what you have to do is that if you have this integration by parts, basically says that if you have two functions, let's say f and g, then we say that we keep the first one of these functions as such, and we integrate only the second part of it. Okay, if this is spanning between 0 to 1, then this was span between 0 to 1, and minus, you just integrate differentiated form of this f and integrated form of this g. Okay, this is what integration by parts means. Okay, Uh, so that's what this is the form that we have used in order to get a reduced order for this u. So after doing this, what you would see is that since we have f dash in this formula, we can see that u double dash has just become u dash, because we have differentiated once, sorry, we have integrated it once. Therefore it has reduced in its from double differentiation, it has reduced to single differentiation, right? So once we have this, now we can actually use a smaller formula, smaller approximation. I mean, we can just take a linear equation in order to approximated polynomial in order to substitute in this uh, differential equation, right? So this is one way to reduce the necessity of having higher degree polynomials. You can just take a linear polynomial by just using integration by parts. So this is all about approximate methods. We have not gone into what finite element means. Okay, so what finite element basically means is that instead of solving this equation through the entire parts from 0 to L entirely, what I can do is I can break down into smaller domains. I can say that I will find the solution. So even in this graph, it might be easier to explain. So instead of trying to approximate, let's say we have a this is the actual function for which I'm trying to approximate. So instead of trying to approximate the whole thing using a polynomial, which might be very difficult, okay, even if you use a quadratic, you might get something like this. If you use a cubic, possibly you might get something like this, and so on. Now what I'll say is, instead of trying to increase the degree of polynomial which I use to approximate this, if I take an nth order, maybe I will be able to satisfy it better. Okay, but then the problem is nth order equations are difficult to solve. So I'll just take a smaller domain. I'll try to solve these things in a smaller domain, right? And then just use linear equations to solve it, because linear equations are very easy to solve. So I'll just take linear fitting curves to solve this as an approximation for this actual curve. So this is what this finite element is all about. So basically we are just taking smaller portions of a bigger structural problem, and then for each part of that problem we are trying to approximate displacement function and then try to find out a solution for it. And we say that how do we know that we are substituting a linear variation is by assuming such a function. Okay, and we have also studied about the concepts of shape functions before, so we'll use that. We can convert, instead of writing it as a plus bx, we could also write it as we have seen earlier, we can, instead of writing this, we can say u is equal to n1 u1 plus n2 u2. Okay, where instead of having a and b as variables, we can have u1 and u2 as variables. The problem with having a and b as variables is that they are not having any physical meaning. A and b are just mathematical coefficients, right? But once we are able to write u as n1 u1 plus n2 u2, then we know that u1 and u2 have some physical meaning associated with it. U1 is the displacement at the point 1 and u2 is the displacement at the point 2, right? So that is the advantage of writing this form in this way. Okay, and how to convert this, we have seen it before. You can uh, we have discussed it already. So where n1 and n2 we call as shape functions, they give the interpolation between both the displacement points, right? Fine, so this is what I wanted to say in this thing, that basically we would use a in finite element, what we are trying to do is that we are trying to find out an approximated answers by breaking a bigger domain into smaller domains, and each domain we are trying to usually fit a linear curve. It is also possible to have a quadratic variation and so on, but then we usually stick to linear approximations, because those are easier to solve using computer algorithms. Okay, so I hope this has given a small flavor of what finite element analysis is, and we will not be going into the details, because anyways when you take the course you will get to see all the details of it, right? Any questions on this?
No.
Okay, okay, then but then we can probably go back to the solving of structure engineering, some
No, no. I had some questions on the course only,
okay.
part of the course. One was the assumptions that was explained in the for the deriving the safe functions of beam element.
Hmm.
Uh, those assumptions I want to clear because in the course maybe I couldn't understand it but better.
Can you state the assumption which for which you are having confusion on?
Assumption one was Euler-Bernard assumption that plane sections remain plane, that is okay, and
Fine.
another one was we are taking the deflection for the top fiber, bottom fiber, and mid fiber same.
Hmm.
From there we were getting a differential equation that we are converting in only one direction. We are converting that only in longitudinal direction. The deflections. The deflections are in x direction and y directions also, but while deriving the same function, we were converting it in only longitudinal direction. That part. I,
Okay. Um,
is it clear?
no,
So yeah.
I don't exactly remember what you're referring to, but then from what you're saying, I'll try to answer. So, for example, what it could mean is that when you have when you say that the deflections of top fiber and bottom fiber are the same in the
Bottom
topward
and middle.
direction.
Yeah.
Yeah, so let's say a beam is assumed to be deflecting like this.
Hmm.
So the deflection, so basically, let's say the initial position was something like this.
Yes.
This deflection is same as this deflection, right?
Yes. Means if you take a straight line at any point, say that only, the middle, top, and bottom. Yes, that deflection is
Yeah,
taken.
so we do expect those deflections to be the same, right? Why is there a confusion in that?
Means
Why do
after
you think that?
we are taking all this as same. Okay, but in case of say deep beam, will it
Yes.
work?
Okay, so then what is the difference in a deep beam and a slender beam?
Uh, Basically, there is one technical statement, but I forgot it. But
Okay.
yeah, deep beam is quite used, so practically you can feel the difference. It
Okay, so
has great depth, so obviously the deflection should be would be different.
okay, so first things first, we don't Euler's Bernoulli theorem is not sufficient, is not fully applicable to D beams, right? In where you have sufficient shear deformations, then actually Euler Bernoulli theorem neglects shear deformations. Okay, so it's not applicable to D beams. But even if you consider thin beams, this is directly from the assumption that you don't have any strains along the uh, depth direction, right? So basically a beam's thickness does not reduce is what this says. When you have the initial thickness of the beam
Hmm.
and final after bending the thickness on the thickness of the beam, we
Okay.
assume that both of them are same. There is no strain along z direction. By z I mean the thickness direction,
The
right?
cross sectional shapes will be conserved.
Yes, the cross sectional depth will not change
Hmm.
before and after bending. Is directly says that the deflection of each of these points is going to be the same,
Be this. Okay.
right? So you can directly you can find this out. It's not very difficult. Even geometry wise, you can show that the deflections of all these points would be same if you only have longitudinals. Basically, from Euler's Bernoulli's theory, what we say is that bending is entirely due to longitudinal strain.
Hmm.
It's just an linear variation of axial strain.
Okay.
There is nothing else in it. No other strains. There is no shear strains. There is no thickness reduction.
Hmm.
All
Hmm.
those are ignored. That is why we can assume that we can safely assume that the vertical deflections of all the fibers will be the same. Not just middle fiber, top and bottom, but
Hmm.
every fiber will be the same.
Okay.
You can one way to think it is you can just think this is one part and it's just bending into one circle here,
Hmm.
and this is one part that is also bending into another circle here.
Hmm.
Both these circles will have different radius, right?
Yes. Yes.
And you can find the center of both these circles.
That has to be
Okay,
seen.
yeah, that will be the same. Now what you can do is that you can find out how much is the difference between this from the geometry, right? So you
Hmm.
have two circles here. You can do this homework and see. This
Okay.
is two circles here, and you find out what is the height difference between this and this point, right? You can keep this length to be some if the initial length was L, then it will be L minus some
Delta.
L dash or delta L. So okay, and this arc will be L plus delta
Plus
L,
delta.
and both of them will subtend angle theta at the center. Okay,
Hmm.
so you have L plus delta L, and see what is this height. you will actually see that the difference between them, this height, initial height, and this height, if you find out the difference, you will see that the
Mhm.
differences will be in the order of second order, not first order. So we
Okay.
usually say that for first order analysis we will ignore those differences and we say that both of the heights are same.
Okay. Okay. And another question was about isoperimetric element. Why
Hmm.
do we require it, and
Hmm.
what is the use of it, and also how do we map it from
Okay.
isoperimetric to the actual element?
Okay, this was given in the assignment.
In the not in the assignment, but
Okay.
it was briefly described in the course.
Okay, described in the course. Okay.
It was just briefly touched that yeah, isoperimetric. It was just introduced.
Okay. So even I'm not fully clear on it, so
Mhm.
possibly I will not. What I'll do is I'll refer back to it and then I'll see what has been said in the course and then I'll put it in the discussion forum. Maybe you
Okay.
can raise a question there itself so that I can also try to address it more
I
formally.
will raise my question there. But
Yeah. What I think is that you have what we do is that if we have a complex geometry, we use a particular uh, interpolation function to assume the boundary itself. That is one of the things that we do. Another
Mhm.
thing is that we assume how the displacements vary between two nodes. So these two interpolation functions are different. Okay, if
Mhm.
both of these displacement functions are taken to be of the same order or identical, then
Mhm.
I believe that element is called as the isoparametric element. But anyway, I'll go
Yeah.
back to it again and then I'll refer and put it, try to give it with more examples so that it will be clear to understand.
Yeah, and the one question from the back of the course
Hmm.
that which has slipped off my mind is
Okay.
you had explained it maybe earlier.
Okay.
That question was why the diagonal elements are positive in a stiffness matrix. Maybe you had explained it using some energy term. Can you explain it
Yes.
once again?
Yes. Why diagonal elements are positive? Diagonal elements are positive from directly from energy, and it also makes sense to uh, assume that they are positive because what are diagonal terms if you think about them? If you
Yeah, in the
have a
same
stiffness,
direction.
yes. So
Yeah,
basically,
actions
it
is in the
means
same.
that what is the deflection that are happening at an ith point due to force at ith point,
Yes,
right? So
it has to be positive there only.
yes.
Yeah, and
So
another thing you had to explain from energy, right? Uh,
yeah, that
Transport
was about determinant has to be positive, right?
determinant has to be positive.
Yeah, because yeah, energy is defined as u transpose ku, and then you have energy to be positive. You know what I mean by this? Okay, so basically we know energy is nothing but F times u, right?
Yeah.
So F times u is what is energy, strain energy, and F is nothing but actually F times u is just scalar form. F transpose u should be the right thing
Mm-hmm.
because F and u will be of the same order, right?
Yes.
So it should be 1 cross n. F transpose is 1 cross n and u is n cross 1. Okay,
Okay.
so then the resultant will be just 1 cross 1. Then what is F transpose? F transpose would be equal to k u the whole transpose, right?
Mm.
So that will be u transpose k transpose.
Okay, transport.
So u energy will be equal to u transpose k transpose is same as k
Mm.
and you have u, right?
Yes.
So now this u transpose ku is what half will be there, okay?
Mm.
So
Yeah. Okay. Anyways, it.
yeah.
Because,
Now since energy is positive, we know that u transpose ku is positive. This should be positive for all the u's. What I mean by that is for any displacement in the structure,
mm.
this strain energy stored will be positive, right?
Yeah.
So which means that independent of this u transpose ku should be positive, which will
Mm.
happen when k is positive definite. In fact, if you see about it, the definition of positive definite of a matrix itself is it's v k. If you check it in net, you will see that it will be v transpose k v should be positive for any v,
Yeah. This I remember. It was shown in the course.
right? So this is another form of saying that k's determinant should be positive.
Okay.
Okay, it's a mathematical proof given that when this
Mm-hmm.
is true for all vectors v, then we can say that determinant of k is greater than 0.
Yeah.
Okay,
Okay.
so that is why since we know that it is positive, we know that k's determinant should be positive.
Mm. Okay, fine. Okay, only these questions were there.
Okay. Okay. So that interpolation function, what is it? Isoparametric. I'll explain.
Isoparametric formulation.
Yes, that only I'll explain it in the discussion forum. Okay.
Okay.
You can maybe post a formal question and then say at what
I will
point they are
post a
discussing
formal
it.
question. You can maybe write it in a paper and scan them.
Yeah, sure.
If, if it is hard to explain in the email.
Yeah. Okay. So shall we discuss the remaining questions that we have
Yeah,
here?
yeah, yeah. You can.
Okay. So I'll just go it a bit faster because we are running out of time. So here we know that the bending moment should be it's hogging, so it will be
Yeah.
negative, right? And then it will drop down again to 0. So the bending moment variation will be like this. And the deflected shape that we would expect is that since there is no bending moment throughout this region, we would say that there is no deflection here.
Mm.
So it would start deflecting only after this point.
Okay.
Okay, so that would be the expected deflection. So basically, it is as good as saying that this part is a fixed end.
Mm.
Okay, this will have similar deflections to that, and the whole part will be straight and rigid.
Cool.
Okay, so that would be the deflected and shape on bending moment for this diagram. And sixth one, can you
It will,
guess what would be the deflected shape?
yeah, from the part of the corner of the beam, it will bend
Hmm.
inward.
It will go inward. Both of these will go inward, right? Because it's like a cantilever subjected to
It's a
end
straight
force.
line.
Since there's a fixed end moment, it will try to bend like this. But only thing the difference between cantilever and this is that in a cantilever, the slope should be zero. But here, slope need not be zero. It can slightly tilt because the topward part also can even. So the reflected shape would be something like this. And since it is bending like this, it will try to give a moment, try to
Yeah.
rotate the top onto as a hogging, and we will have this thing. Okay. So this is a curved, it's not straight. It's similar
Mm.
to a cantilever. If you take a free body, it's just load and moment which is trying to rotate it clockwise. So I'll have an anti-clockwise moment. Okay.
Mm.
This will be the case.
This is the another one was I think interesting. Seventh number.
Yeah. So here it's a slightly tricky problem. So what is a uh, deflected shape that we would expect? We know that there cannot be any horizontal forces here, right?
Mm.
Because the total, if there is a horizontal force at this hinge, it should exist here also, but it cannot
Yes.
exist in a roller. Therefore, the horizontal forces itself should be 0. If horizontal forces are 0, then the vertical columns will never have a curvature in it because only the horizontal force can give rise to a moment at a point. Right?
Yes.
This into x will give a moment, and that will be satisfied by a moment here. But then, since there are no forces, horizontal forces here, we know that this cannot bend. If this cannot bend, then what should be the deflected shape? We know that this has to bend like a simply supported beam, partly. So
Mm.
if it bends like a simply supported beam, the problem is that since in order to satisfy the rotation here, we need to have something like this.
Yes.
And it has to be 0 again here, which means that it has to curve, right? So it cannot curve. So the only way it cannot curve and still it has to bend here is what should happen? Any guess?
It should go rightward. Sway.
Yeah, so what should happen is that we know that the simply support has to go like this. Then only we know that the angle here 90 degree can be maintained without any curvature, being a straight line.
Yeah.
This 90 degree can still be maintained. And for this 90 degree to be maintained, it has to go away because the rotation is like that, right? So that means the roller has to move.
No.
So this is the deflected shape, right? And this part will behave like just like a simply support. There is no difference between the bending moment here and a simply support.
Mm.
Right, so it will just be PL by 4. That's it. This is the bending moment shape for the frame.
Yes.
Okay, and what about this?
Uh, column should bend. Beam should not.
So what we know is that this H will be entirely given resisted by this H, which means that there will be some curvature in this column because
Yes.
when horizontal forces come, definitely we have a bending moment. So we know that it's going to bend. There will be some moment here. There will be another moment here. So we know that since it's getting pulled, this point should definitely move towards
Move towards
left,
right.
towards right. So the reflected shape we can draw is, let's say the roller has moved here. Okay, we know that if you think about this thing, it's just a cantilever,
Mm.
similar to a cantilever with this load, right? So the curvature would be something like this,
Yes.
right? So that's what you need to draw, not the other way. You should not draw it like this. It's
Yes.
like a cantilever. If this was a cantilever, then it should be something like this,
Yes.
right? So that is what you need to be careful about. Okay, so that's how the reflected shape would be, right? And what about ninth?
Uh, the beam will
Hog.
hog, and
Yes.
there will be similar deflection here.
So will there be a horizontal force here? No, we cannot have, because if horizontal force is there, then it cannot satisfy the entire equilibrium of the structure.
Mm.
It cannot cancel, right? So there is no horizontal force, means that this is not going to bend. If this is not going to bend and still it has to hog and maintain 90 degree, the only way is to move towards left. Then only you can have this 90 degree,
Mm.
right? If you would have drawn it here, hogging like this, then this cannot be straight because this will
Yes.
not maintain 90 degree. That is what you need to remember while drawing it. Okay, so this is how it will move towards left.
Mm.
This will maintain 90 degree. Okay, what about 10th one?
This
10th
one
one is
simple.
similar to what we did earlier. It will behave like a simply support. Now we can have two forces coming here, therefore both can bend, which means that I can have a deflected, a bend shape in this.
Yes.
Okay, so that is easy. Now what about 11th one?
Think there will be difference in slope in the beam.
Yes,
It will
so
slightly sway towards right.
yes, this will also, we know that it's going to behave something like a bend. By the way, here, even though we are saying this will behave like a simply support, the difference is that there will be some end moments developed. Okay,
Yes.
so it is partly between fixed and simply support.
Yes.
Okay, so you cannot just say that this is PL by 4.
Mm.
But here, what we know is that the moment here should be 0. If
Yes.
bending moment there at that point is 0, and that means that if we consider about this column cannot have any horizontal forces, because if it has horizontal forces, then
There
it
is
has to be
mm,
cancelled by a moment here,
yes.
bending moment here, which is not existing. It's 0. Therefore this horizontal forces cannot develop. Okay, that means that we this cannot bend. Okay,
Yes.
if there is no horizontal forces here, there is no horizontal forces here as well, because in the total structure only one side we cannot have horizontal forces,
Yes.
right? So that is why both these columns cannot bend now. Now we know that this has to bend something like a simply support. So the only way that can happen is it has to move towards left and then bend like a simply support, so that this will be 90 degree, and this need not be 90 degree because we know it's a hinge.
Yes.
That is all.
Okay.
Okay,
Okay.
that is all. Okay, good. So then probably we can stop it for today, right?
So I
Okay.
think this is my goodbye.
What is it?
I think this is goodbye. Last class, no?
Yeah, yeah. We will probably meet in some other session if possible, or we will anyways be discussing the discussion for forum, right? Okay.
Okay.
And all the best for your examinations, too.
Yeah, I do have exam next week.
Yeah.
Thank you.
Okay. Yeah. Sure. Thank you. Thank you for attending.